Good afternoon, everyone. I'm Karan Ahuja, a third-year PhD at Carnegie Mellon University. Today I'm going to be presenting my work on LightAnchors. This work was done with the amazing collaboration of Sujeath Pareddy, Robert Xiao, Chris Harrison, and Mayank Goel. So we have already heard a bit of motivation from Jackie, so I'm not going to spend too much time on it, but I'll just briefly go over it. Augmented reality requires overlay of digital information and interactive content onto scenes and objects. This creates the need for fast and robust in-view anchoring and data transmission. While we expect this transfer of data to be seamless, in reality, it often requires marker tags that are large and pronounced. For example, large QR codes and trains that transmit their schedule, or Ahuja codes and art galleries that help us to do image overlays on top of them. Apart from being visually obtrusive, these tags can also transmit only a fixed data payload. Alternatively, another approach is to pre-scan the environment with markerless techniques. For example, this is the Apple ARKit object registration pipeline. So first you have to scan the object, define a bounding box around it, and after you scan it, you can adjust the origin of it and then export it so that other people can use it. But as you can see, this process is very tedious and time-consuming, and every time you move into a new room, you have to do this again and again. So what we ideally want is a system that requires no pre-registration and no special instrumentation of objects. It should also be unobtrusive, or at least attractive. We also want the ability to do many simultaneous object recognition together, while having no handshake and this being in a completely cloudless environment. We also want the ability to support dynamic data payloads, all at the same time having a downloadable app for a smartphone so that everybody can use it in a software-only approach. So let's go over how we can do this. So we notice that many devices around us have some sort of status LEDs on top of them. For example, the smoke alarm mounted to the wall uses lights to tell the user about the smoke status in the room, or this power strip relays state information through the LED below its switch. Keep in mind that these devices have no internet, Bluetooth, or any connectivity with the outside world. It would be great if we could give these dumb devices a voice in the AR world in a completely cheap and cloudless manner. Another interesting development over the last years is in the camera space technology. In recent years, cameras have come up with leaps and bounds. A particularly interesting development is the prevalence of high-speed cameras, which have become commoditized. These can not only capture at 240 frames per second, but also process data at real time as well. Thus, utilizing the pervasiveness of point light sources and high-speed cameras, we developed LightAnchors, a new method for displaying spatially anchored data. Unlike most prior tracking methods, which instrument objects with markers, we take advantage of these lights, such as LEDs and light bulbs, for both in-view anchoring and data transmission, as can be seen in this payment terminal example. So we are not the first ones to think along this direction. LightAnchors overlaps with several different literature. We will now briefly look at different parts of this research areas. So in terms of marker-based strategies, there have been approaches that use fiducial markers and QR codes, such as AR tags and Ahuja tags. There have also been approaches that use custom patterns and overlay those custom patterns with information based on their known placement in the environment. Markerless strategies rely on computer vision, such as registration in paper snap to it, in which they pre-register the object and then detect the object, and based on that load a specific web page. Or in Vuforia, where they pull up an information in a pre-scanned markerless environment. In the visible light communication domain, there have been approaches that use the mobile's photodiodes to transmit information and communicate between devices, and also approaches that use the rolling shutter of the camera to sort of transmit data. But all these approaches cannot localize the source and rely on a single light in a particular room, and cannot scale well to simultaneously transmitting light sources. So now let's go over the implementation step of and the algorithm of LightAnchors. So for every incoming frame of video, we create an image pyramid such that lights big or small, close or far, are guaranteed to be 1 pixel at size at one level. Our algorithm then searches for light anchors using a max pooling template that finds bright pixels surrounded by darker pixels. This process produces many candidate anchors, such as the buttons on a keypad, which are also light in color, surrounded by darker material, as you can see over here. To filter these, we track these candidate anchors over time, looking for a blinked binary pattern. Only candidates with the correct preamble are accepted, after which we can decode their payload. As high-speed cameras are now becoming common in smartphones, our approach can run at very high frame rates. On the iPhone X, our process runs at 120 frames per second, allowing us to decode a 32-bit light anchor in roughly a quarter of a second. Now I'm quickly going to switch over and try to get and show you a live demo of the system working. Just give me a second. Let's see. Okay. Yeah. Wait, just give me a second. Yep. There we go. Okay, great. Sorry for the delay, guys. Okay. So now, this is the live play. So now you can see the camera feed. Let me take you through this step by step. So here you can see the candidate light anchors that are being transmitted. Now these are all the candidate detections of the light anchor. Now I'm going to show you the tracking phase of the algorithm. As you can see, the light anchor that is on the conference phone over here, the green LED, if I move it, it is tracked over time. Now once we detect it and track it over time, we can also decode its payload. So this shows the decoded payload. Wait. Yep, this will show the decoded payload of this light anchor. And then we can also use this information and also show an example application on top. Like we can see that this is a conference phone. Or, okay, yep, we can see this conference phone. The light is not long enough, sorry. So for the further demos, please come to our stand and I'll show you the demos in person. This cable is not long enough, and if I extend it, I guess it will snap. Okay. Now let's go over the evaluation protocol of our system. So what we do is we use an iPhone 7 sampling at 720p and 120 frames per second for our system. We evaluate our system in 3 environments: a workshop, classroom, and office, across 3 lighting conditions: lights off, artificial lights only, and artificial light with diffuse sunlight. We capture this data across 2 motion conditions: still and walking. All this across 6 distances ranging from 2 meters to 12 meters. We do this for 2 LED sizes to see the effect of size on our data capture rate, which are 3 millimeter LED and 100 by 100 millimeter LED matrix. We find that for the detection, we designed a system such that it has high recall. The rationale was that bright light sources can be filtered with the preamble matching step. We see that our true positive rate for our system is 99.6%. And we found that most false positives were actually caused by the reflections of the light anchor that is already being blinked in the system, and that's why it showed up with the correct payload as well. So what we do to encounter this is we take the payload with a higher signal-to-noise ratio. Across all conditions and distances, we found a mean bit error rate of 5.2%, which roughly means 1 in every 20 transmitted bit was incorrect. This level of corruption can typically be handled by error correction techniques. We can see from this graph that light anchors perform better when there is low ambient illumination, since the light anchor is brighter compared to the background. Also, when we see the performance across light sizes, we see that bigger light anchors can be detected from a further distance, and this is due to the lower SNR ratio. We also found that the performance is better for when the person is still rather than walking, because there is motion blur when the person is walking. So across all conditions, we found a mean recognition time of 464 milliseconds. As our light anchors are 22 bits long, they take a minimum of 103 milliseconds to transmit at 120 FPS. Because there is no synchronization, detection of a light anchor is almost certainly going to start in the middle of a transition, meaning that the system will have to wait and retransmit again after a change in phase for a correct decode the next time. So let me conclude with some example use cases. First and more straightforward is to transmit fixed data. For example, the name of a building and its opening hours. More interesting is the ability to decode a small dynamic payload. For example, this glue gun provides its current temperature. And this power strip provides its live temperature draw, while the smoke alarm shows its battery life. Apart from just instrumenting the devices and instrumenting them with microprocessors, many devices existing today already have microprocessors that can control status LEDs inside them. We can now exploit these and use them to transmit dynamic data. You can imagine a scenario in which you walk into your Starbucks cafe and it has a router mounted on the side of it. You just point your phone towards the router and click on the connect button after you see the light anchor, and you can connect to it through the guest Wi-Fi. So this way, you are the only one who can connect to it, and sort of nobody else can steal the internet in Starbucks because you're physically located in that space and have line of sight. Similarly, a security camera can share its privacy policy. So whenever you walk into a building and you have the security camera, you can point to it and see whether it's recording audio, video, or whatever the case it is. So light-anchored payloads can also be used to provide connection information. For example, let's take the case of this thermostat. And once you're using a light-anchored payload, you can simply point your phone towards it, and this can open a gateway towards a Wi-Fi connection or something else. Now it can send over a little app through which you can actually control your thermostat. For example, over here you can see me increasing the temperature. A similar example holds for smart light switches, where it can provide you with an IP address, allowing you to open a socket to your light bulb. And there is no need for any tedious IoT pairing anymore. So we are currently open source. Our iOS app is open source. Please email me and I will send you a test flight link. There's also starter code for Arduino, and there's more information on the LightAnchors website. And also, please come and see our demo today at the demo reception, where we'll be showing these and more demos running real time. So thank you, and now I'll take questions.
Thank you.
Hi, Karan. Thanks for the talk and bonus points for the live demo. Always appreciated. Can you talk a little bit about discoverability? Right, you said you wanted the things to be attractive in your opening statement, but then we're pretty well conditioned to scan QR codes and whatnot, and we're also pretty well conditioned to ignore the status LEDs in most of our devices.
That's a very good question. So, yes, we are. So what I'm imagining is a case where most of these devices are already augmented with these. So it will be as simple as when you take over your device in this markerless AR world. You do not know where the markers are anyway, right? It's the same as sort of that markerless strategy, but now instead of this markerless new environment, it's the LED which provides you that experience.
Thanks for your talk. Can you talk a little bit about authentication? So communication flowing the other direction. Let's go with a thermostat example. Mm-hmm. Maybe in my home, it's realistic that anyone who has physical access to the thermostat can change the temperature. But in like an institutional setting, that's not true, right? Only the building manager should be able to change the temperature, and not anyone who walks into a classroom or this room.
Oh, that's a very good question. So actually what I'm more envisioning is, for example, in a home use case scenario, you can have no security settings. So the idea is once you connect to it, or once you have this connection payload, it opens a web page. And in that web page, you can imagine and asks you for maybe your Wi-Fi, or for your credentials to log on to it.
Thank you.
Question: How long is your payload, and how would you imagine, for example, the privacy policy to be transmitted from a camera?
What was the second part, sorry?
So the first part is how long is your payload for your packet, and how long does the packet take to transmit, and then how would you imagine the privacy policy to be transmitted from the camera?
So our data, let me answer that question in bits. So we have a 6-bit preamble and then an 8-bit data payload in our current implementation. And it takes roughly, and we have a latency of around 1/3 of a second currently. And in that privacy policy, I'm assuming you're talking about the example application. So the idea is simple, that you point your phone towards the camera, and based on that, the camera will transmit to you the privacy policy. It can be, for example, that, hey, I'm a security webcam over here, I'm blurring faces, I'm not storing any of your data.
One of the things is with 8 bits of payload, it's really hard to transmit the entire privacy policy.
Yes, that is very true. So the idea is that with the 8-bit payload, you can open another connection through which you can send more data. Or we are also working on another implementation in which we can transmit at higher frame rates. So you can imagine once you have at least 3 or 4 bytes, or you can transmit over a longer period. That way you can transfer more data towards it.